In the wavelength and frequency lab that you guys just completed, you looked at the relationship between the wavelength of a periodic wave and the frequency, the number of cycles per second used to create that periodic wave. In the lab, you guys used a simulation to vary the frequency of disturbance of a string, and you measured the length of the wave, the distance from crest to crest, or the distance from trough to trough. So in this video, I'm going to look at a little bit of your data and some of your preliminary analysis, and then we're going to talk about what kind of conclusions we can reach about the relationship between the wavelength and the frequency of a created periodic wave. So here's some data and some preliminary analysis for a data set that was collected using high tension in the string. So they graphed the wavelength versus the frequency, and they got a hyperbolic relationship. As the frequency increased, it was shaken at a faster rate, more cycles per second. Looks like the wavelength decreased. In order to write the equation for how wavelength and frequency are related, looks like they linearized their graph. So they inverted the frequency on the x-axis, and it looks like they got a straight line. That line of their linearized graph had a slope of about 5.1 centimeters per second. Their y-intercept was about 0.6 centimeters, fairly close to zero. So their equation looked like this. The wavelength is equal to the slope, which is about 5.1 centimeters per second, times the inverse of the frequency plus 0.69 centimeters, their y-intercept. Remember, 1 over f shows up in your equation, or the inverse of the frequency, because that's what was graphed on the x-axis for your linear graph. It was the inverse of the frequency. So in place of x, you got the inverse of frequency. Let's look at another data set and analysis. So here's some graphs and an equation for a data set collected using medium tension string. Some of you guys might have collected low tension string, but it looks like they also found an original hyperbolic relationship between wavelength and frequency. So seems like all the data I looked at, there was a hyperbolic relationship, so we can conclude that there is a hyperbolic relationship between the wavelength of a periodic wave and the frequency used to generate that periodic wave. They also inverted the frequency values and graphed on the x-axis to get something that looked linear. And the equation for that line was wavelength is equal to a slope of 3.5 centimeters per second times the inverse frequency plus 0 centimeters. So let's first talk about the y-intercept. If we look back at the first student's data, they got a y-intercept of about 0.69 centimeters. In the second student's data, they said their y-intercept was 0. I'm assuming they approximated that to be 0. So the question is, would we expect there to be a y-intercept? Now, several of you guys said that if the frequency is 0, which means the string's not being disturbed, we would expect there to be 0 wavelength. We have to be careful though. If there is no frequency, if the string's not being disturbed, we're not creating periodic waves, and we can't even measure a wavelength. So let's talk about what happens as the x variable here, inverse frequency approaches 0. What would we expect the wavelength to approach? Well, how could you get this value, the inverse of frequency, to approach 0? Well, frequency would have to be larger and larger and larger. So as frequency increases, the inverse of frequency will decrease. And as the frequency gets really, really big, that means it's, there's a very high number of cycles per second. It's going to be shaking back and forth or being disturbed at a very high rate, a lot of cycles per second. We know that the wavelength would decrease. Like, look at here. As frequency increases, what do you notice? The wavelength is approaching, as we increase frequency, it's approaching a value of 0. So on our linear graph here, as frequency approaches a very large value, 1 over frequency would approach 0. And as that approaches 0, we would expect the wavelength to also get really, really small, approaching a 0 value. So we can reason that the y-intercept should be 0. Now let's talk about the slope. The first group had a slope of about 5.1 centimeters per second. The second one had a slope of 3.5 centimeters per second. These are both slopes of the line. And remember, if we have a slope of a line, the slope of a line is constant. So that number or these numbers, 5.1 centimeters per second and 3.5 centimeters per second, must represent something or some things that stayed constant in the experiment. Well, we've got values to look at, we've got units to look at, and the fact that it must represent something that stays constant. So let's look at the units first. We get centimeters per second. And that's the unit for what kind of a value? That's the units for basically a speed or a velocity. Was there a speed or velocity that stayed constant throughout the entire experiment? Yeah. In each of your experiments, no matter how you chose to disturb the string, the speed of the pulses or the periodic waves moving through the string was constant. Why? Because you kept the tension constant in the string. Remember that tension affects the velocity of the pulses or the periodic waves moving through the string. And so if you had a high tension, it should have been moving at a high velocity. If you had a medium tension, they should have been moving through at a medium speed. If you had a low tension, they should have been traveling very slow through that string. So it seems like the slope might be related to the velocity of the waves moving through the string. In the case of the high tension string, were the waves moving through the string at about 5.1 centimeters per second? And in the case of the medium tension string, were they moving through at about 3.5 centimeters per second? Well, we can go back to the simulation and find out how fast were the pulses or periodic waves moving through the strings. So here I have an animation on the left showing a single or individual pulse moving through the string at high tension, medium tension, and low tension, and they're started at about the same time. And just as a review, you can see, like we've already figured out, that the higher the tension in the string, the faster the individual pulses or the periodic waves will be moving through that string. So I've paused this simulation to show what the displacement of each of these pulses were after a time of exactly 1 second. And so in 1 second, the high tension string, that pulse moved about 6 centimeters. So if it's moved 6 centimeters in 1 second, that pulse, or the wave, is moving at a speed of about 6 centimeters per second. For the medium tension string, it looks like it had a displacement of about 3.6 centimeters, and that happened in a time of 1 second. So it must have a wave speed of about 3.6 centimeters per second. Remember, the data we looked at, the equation had a slope of about 3.5 centimeters per second. So that's really close to how fast the speed is. So it looks like the slope of a wavelength versus frequency graph is the wave's speed. How fast an individual pulse moves through the string, or how fast the periodic pulses are moving through the string. So now we can reach our final conclusions about the relationship between wavelength and frequency. So here's a sample equation. Let's say for a high tension string, we get an equation that looks like this. Wavelength is equal to about 6 centimeters per second times the inverse of frequency. And remember, we said the y-intercept is insignificant. We kind of reasoned that away. Well, this value, we just got done talking about the fact that it's how fast the wave is moving through the material or the medium. So we call that the wave velocity or the wave speed. So we get wavelength is equal to the wave speed times the inverse of frequency. Or we can just multiply these two things together and we get this final equation that wavelength is equal to v divided by f, or wave speed divided by frequency. Now that we have this general equation, we can use it to figure out how all three of these variables are related to one another, how wavelength, frequency, and wave speed are related. So if you look at the animations to the left, I have each of the three strings at different tensions. On the top it's high tension, in the middle it's medium tension, on the bottom it's low tension. If you look on the left-hand side, the thing disturbing each of those strings at different tensions are shaking back and forth kind of at the same rate. It's introducing the same number of cycles per second to each string, so they're being disturbed at the same frequency. So if we look at our equation, what happens if frequency remains constant in all three of those situations? Well, then it looks like the wavelength is proportional to the wave speed. So the higher the wave speed, the higher the wavelength. Is that the case in our animations? Well, let's look. At the high tension string above, we know the waves are moving the fastest through that material, and you can see it moving the fastest from left to right. And for a higher speed, it does have the largest wavelength. If we go all the way to the bottom, the lowest tension will have the lowest wave speed. They're moving the slowest through our material or our medium. And notice they have the shortest wavelength. There's the shortest distance from crest to crest. And that makes sense. If we have something disturbing the material, and if each part of that wave is moving away at a faster speed, by the time the thing doing the disturbing makes it all the way up to another crest, or to make another crest in the periodic wave, the first crest will be further through the string, therefore the wavelength will be larger.